The final message from Earth is 11 seconds long. Then the channel goes quiet, and it stays quiet. No more cargo, no more crew, no more engineers talking a broken pump back to life at 3 in the morning. On Mars, a few hundred people are suddenly the entire human supply chain. They have oxygen machines, water recyclers, greenhouses, a nuclear reactor humming in the dark. For a while, none of that matters, because they are already dying slowly, quietly, in a way no alarm will catch. The question is not whether they can breathe tomorrow, it is what they run out of that they can never make again, and the answer is stranger than running out of air. What breaks first is not one lung but a whole civilization. If these kinds of deep dives are your kind of thing, tapping like and subscribe genuinely helps our channel keep making them. Now, settle in, get yourself comfortable, let's begin. The last message from Earth does not sound like the end of the world. It sounds like paperwork. A routine status packet, a few lines of telemetry, a half-finished note from a flight controller who fully expected to write another one tomorrow. Then, nothing. The next scheduled contact window opens and closes empty. So does the one after that, and the one after that. On Mars, the dish antennas keep turning, keep listening, keep pointing themselves at a pale blue point of light that is still, technically, home. The signal simply never comes back. We are not going to spend this story asking why. That is the version everyone expects, and it is the wrong version. Whatever happened on the other end, a war, a slow collapse, a quiet administrative death that no one on Mars will ever be able to name, the decisive fact is not the cause, it is the consequence. No more instructions will ever arrive. No more cargo landers will ever drop out of the pink sky with fresh filters and spare pumps in their bellies. No more replacement crews will ever step down a ladder, carrying new hands, new training, and new knowledge in their heads. The umbilical that fed this settlement for its entire existence has been cut, and it is not going to grow back. Here is the first surprise. On the day the signal dies, nobody on Mars is in any danger at all. The lights stay on, the air stays sweet, dinner is served on time. If you walked the corridors of the habitat that evening, you would see people arguing about the duty roster and complaining about the texture of the algae, exactly the way they did the week before. The disaster is completely real, and it is completely invisible, because the thing that just broke was not a machine you could point to. It was a relationship, a supply line stretched across as much as 400 million kilometers at the worst alignment. A line everyone had quietly assumed would always be there. Part of why the silence hides so well is that talking to Earth was never instant to begin with. Even at their closest, the two worlds sit tens of millions of kilometers apart, and radio, fast as it is, still takes minutes to cross that gap, 3 or 4 minutes each way, when Mars and Earth ride near one another, stretching to as much as 22 minutes each way when they swing to opposite sides of the Sun. A question asked of Earth might wait the better part of an hour for its answer. So the colonists had long since given up on conversation and learned to live by exchange messages sent, messages received, like letters carried across a widening sea. When the letters stop, there is no dropped call, no deadline to jolt anyone upright. There is only a reply that is late, and then later, and then one day simply never comes. The catastrophe arrives disguised as ordinary delay, and that disguise is the first of many reasons no one panics. To work out how long these people can last, we have to be brutally precise about what the question even means, because there are two different questions tangled together inside it, and they have wildly different answers. The first question is simple: how long can the colonists stay alive? The second is deeper: how long can the colony stay a colony? Those are not the same thing, and the entire distance between them is where this story actually lives. Keeping a group of humans breathing for a while is, relatively speaking, the easy version of the problem. A sealed habitat stuffed with stored supplies behaves a little like a very sophisticated submarine. It can keep its crew alive, cut off from any friendly port, for a remarkably long time, as long as nothing essential wears out and nobody opens the wrong hatch. But a submarine is not trying to become a nation. It is not trying to grow all of its own food forever, manufacture its own circuit boards, deliver and raise a next generation, and rebuild every pump, seal, and filter it will ever need out of raw rock. A colony that wants a future has to do every single one of those things. The moment Earth goes quiet, the settlement stops being an outpost of a civilization and is asked, with no warning and no vote, to become a civilization from scratch. Those are two different jobs, and this is the whole point. They fail at two very different speeds. So before we start any clock ticking, we have to define exactly what we are timing. A survival estimate that does not describe the colony is worthless, because the answer swings by decades depending on who and what we are actually talking about. Let us build one specific, honest reference colony and hold it fixed for the rest of the story. Not a gleaming fantasy city of glass domes, and not a lone explorer in a tent, but something in between, a mature early settlement of the kind that engineers and space agencies actually sketch when they are being serious instead of cinematic. Give it 250 people, that number is chosen carefully. It is large enough to run shifts around the clock, staff a small clinic, teach a handful of children, and hold a reasonable spread of skills. Physicians, reactor technicians, machinists, electrical engineers, agronomists, a couple of people who genuinely understand chemistry. And it is small enough that every single person is load-bearing. In a town of 250, there is no such thing as a redundant specialist. If the only two people who truly understand the water plant both fall ill in the same month, an entire capability of the colony flickers and threatens to go dark. Remember that number, 250, because population is not a background detail here. It is one of the master variables that decides everything downstream. Now decide where on Mars to put them, because that single choice quietly shapes everything that follows. Mars offers no free lunch on real estate. Every site is a compromise between two kinds of danger. Go toward the equator, and you get the planet's mildest temperatures and the strongest sunlight for the solar arrays, but the near-surface water ice thins out and retreats deeper underground, and the colony's most basic raw material becomes something it has to chase downward through meters of rock. Go toward the poles and the ice grows abundant and shallow, close enough that a well-placed shovel could almost reach it, but the cold deepens, the sunlight weakens, and the winters lengthen toward months of gloom. Our colony splits the difference and settles in the mid-latitudes, somewhere around 40 degrees from the equator, on a broad plain where orbital surveys have mapped a thick sheet of buried ice beneath a shallow blanket of soil. It is a crossroads address, chosen to keep water within reach without surrendering entirely to the cold. That decision, security of water, bought at the price of warmth and light, is exactly the kind of trade every part of this settlement was assembled out of, and it will echo through every clock we are about to start. Now house them. Put the habitat underground, or very nearly so, buried under a few meters of Martian soil, the loose, rusty, broken rock called regolith that covers the whole planet. This is not decoration. Mars has almost no magnetic field, and only a wisp of an atmosphere, less than 1% of the air pressure you are breathing right now, so the surface is soaked in radiation that Earth's thick air and magnetic shields spare us from completely. Piling regolith over the living quarters is the single most reliable defense the colonists have, and it is a genuinely solved problem. Mass stops radiation, and Mars has a limitless supply of mass. So our colonists live in shielded, pressurized modules, warm and shirt-sleeved on the inside, while the world outside sits at around minus 60 degrees Celsius on an average day and plunges far colder at night. Every wall between them and that cold is holding back a pressure difference that would kill an unprotected human in minutes. Those walls, and the seals that join them, are going to matter enormously later. Hold that thought. Give the colony its heartbeat, power. Our settlement runs on a fission reactor in the 40 kilowatt class, the same rough size that NASA and the Department of Energy are actually developing right now for the Moon and, eventually, for Mars. In December of 2024, NASA formally committed to using nuclear power on the Martian surface, and for good reason. Solar panels are wonderful until a planet-wide dust storm blots out the sky for weeks, or until the long night falls, or until fine dust settles on the panels and slowly chokes their output. A reactor does not care about any of that. It hums along day and night, through storms and darkness, turning the steady heat of splitting atoms into steady electricity. We will be generous, and give our colony a little more than one reactor's worth, because studies suggest that sustained human operations really want at least 100 kilowatts to run life support, mining, and manufacturing all at once. So, reliable, weatherproof power with solar arrays as a daylight supplement. This is the beating heart, and as long as it beats, the colony has a chance. The day it stops, almost everything else stops with it, a dependency we will come back to. Now the two systems that keep the people alive. Breath to breath, air and water. Our colony inherits the best closed-loop life support technology humanity has ever built, the descendants of the machines flying on the International Space Station today. And here we have to be careful and precise, because this is exactly the kind of place where a Mars story usually cheats. Start with air. The colonists are not breathing bottled oxygen shipped from Earth that ended long ago. Their oxygen comes from two sources working together. The first is water. Run an electric current through water and it splits into hydrogen and oxygen. That oxygen goes into the air, and this electrolysis is proven, routine, everyday technology that has kept station crews breathing in orbit for years. The second source is the Martian atmosphere itself, which is about 95% carbon dioxide. On the Perseverance rover, a microwave oven-sized instrument called MOXIE did something genuinely historic. It pulled that carbon dioxide from the thin Martian air and stripped oxygen right out of it, the first time any resource has ever been harvested from the surface of another planet for human use. That is a confirmed, demonstrated milestone, and it deserves the applause. But keep the scale honest. Across its entire mission, over a full Martian year, MOXIE produced a grand total of 122 grams of oxygen, roughly what a small dog breathes in 10 hours. At its best, it made about 12 grams an hour. To feed a town of 250 people, you would need a descendant of MOXIE built perhaps 200 times larger, drinking tens of kilowatts of that precious reactor power without pause. Our colony has exactly such a plant, humming away, turning Martian air and reactor electricity into breathable oxygen, and, as a bonus, into rocket propellant. The physics works, the chemistry works. Remember, though, that the plant is a machine, and machines are the theme that is quietly stalking this entire episode. Then there is the exhaled carbon dioxide inside the habitat, which has to be scrubbed out of the air before it builds up and poisons everyone. That too is solved technology, cycled and regenerated rather than thrown away. Air, in other words, is arguably the colony's strongest single card. Between electrolysis, atmospheric processing, and carbon dioxide scrubbing, the settlement can, in principle, keep making breathable air out of local ingredients and electricity for as long as the electricity and the machines hold out. Water is nearly as strong, and it leans on two pillars. The first is recycling, and the numbers here are astonishing and crucially real. On the space station, engineers have pushed water recovery to about 98%, capturing humidity from the air, reclaiming wash water, and yes, distilling and purifying urine back into water, cleaner than most of what comes out of a tap on Earth. Nothing is wasted. Almost everything is caught and used again. Our colony runs a plant descended directly from that one, closing the water loop to somewhere between 90 and 98%. The second pillar is raw stock from the ground. Orbital surveys, the subsurface water ice mapping project. Chief among them have confirmed vast quantities of water ice buried in the Martian mid-latitudes, sometimes shallow enough that a fresh meteorite strike punches through and exposes bright ice at the surface for the cameras overhead to catch. This is not speculation. The ice is really there, and there is a staggering amount of it. Our colonists deliberately settled near one of these buried deposits. So the water story reads beautifully on paper. Recycle almost everything you have, and top up the losses by mining ice from the planet itself. And then food. Our colony grows crops in pressurized greenhouses under electric light, using hydroponics and aeroponics plants fed by nutrient-rich mist and water rather than soil. On the space station, astronauts have already grown and eaten lettuce, radishes, and chili peppers, so the basic act of raising a plant off-world is a demonstrated fact, not a dream. Beyond the greenhouses sits the colony's deepest cushion of all, a warehouse of stored, shelf-stable food freeze-dried and vacuum-sealed, along with vitamins, medicines, and a library of seeds. The planners who built this place, back when Earth still answered its calls, stocked it deliberately for emergencies. Call it several years of core calories in reserve, sitting quietly in the dark, waiting. Add all of that up, and you get the reference colony we will follow to the end. 250 people, buried in shielded and pressurized habitats, powered by a nuclear reactor, with solar backup, breathing air made from local resources and electricity, drinking water recycled at up to 98% and topped up from buried ice, eating from greenhouses backed by years of stored food, with a plant that turns the atmosphere into oxygen and fuel, plus a workshop of three-dimensional printers and machine tools, and a hoard of spare parts, medicines, and seeds. By any reasonable standard, this is an impressive settlement. It is exactly the kind of place a proud mission report would describe as a foothold, a beachhead, the beginning of humanity's second home. It is also, on the day the signal dies, entirely dependent on Earth, and almost nobody living there fully realizes it yet. To understand how a place this capable could also be this fragile, you have to know how it got here, because the colony did not arrive in a single triumphant landing. It accreted, the way a coral reef builds itself layer on layer, over decades, each new arrival cemented onto the hardware left by the last. First came robotic landers that made a little fuel and scouted the ice, then a handful of pioneers in a cramped module resupplied constantly from home, then more habitats, more greenhouses, a backup reactor, the first children born under the regolith. Every expansion was a triumph, and every expansion was paid for by Earth, each new machine flown in finished, each new specialist trained across the void, each shortfall quietly covered by the next cargo lander in an endless, dependable stream. And here is the irony baked into the settlement's whole history. Growth did not reduce its dependence on Earth, it deepened it. A bigger colony needed more filters, more spare boards, more medicine, and more specialized parts than a small one, and every one of those still came from the same blue point of light in the sky. The colonists mistook getting bigger for getting self-sufficient. Those were not the same thing. They were, if anything, opposites. The settlement had spent decades growing more elaborate, more populous, and more comprehensively tied to a supply chain it did not own right up until the morning that supply chain vanished. For the first days after the signal died, the colony did what people do. It waited. Surely this was a glitch, a solar storm garbling the link, a fault at a ground station that some engineer on Earth was already cursing over. The antennas were checked and rechecked. Backup frequencies were swept. The colony's own transmitters kept sending status reports, then queries, then eventually pleas out into a silence that returned nothing. Days became weeks, and slowly, without any single moment of announcement, the waiting curdled into understanding. There would be no reply. Whatever the colony was now, it was that alone. The leadership for a settlement this size has a leadership, a director, and a council, and a chain of decisions gathered, and did the only sensible thing, which was to take stock, count the food, count the spares, count the medicine, measure the reserves against the mouths and the machines. And the first count came back reassuring, which was itself the most dangerous thing about it, because it let everyone believe the problem was a problem of supplies, of numbers in a warehouse, when the real problem had no inventory line at all, and what a reassuring count it was, on its face. The food store held something close to 3 years of full rations for every soul in the colony, and more if they stretched it, quite apart from whatever the greenhouses would keep bringing in. The clinic's shelves carried a deep stock of the common medicines, the antibiotics, the painkillers, the anesthetics, enough that no one doing the counting felt any flicker of alarm about the months just ahead. The spare parts bins told the same soothing story: pumps and fans and valves in tidy rows, replacement seals and filters by the 100, drawers of controller boards for every critical system, a few of the most failure-prone machines backed by a complete spare unit still sealed in its shipping wrap. There was a buffer of pre-treatment chemicals for the water plant measured in many months, tanks of buffer gas held in reserve, boxes of filter cartridges stacked to the ceiling of the supply module. Written down line by line, it read like the inventory of a settlement that could shrug off almost anything. And that is precisely the trap the numbers laid, because every single figure on that list shared one hidden property that no column in the ledger recorded. Each named a store to be spent, never remade. Not one line could be replenished from the sky, or, for most of them, from the planet. The count measured how much the colony had. It could not measure the thing that actually mattered, which was how much the colony could make. And that number, the one nobody wrote down, was very nearly zero. So let us play the tape forward and watch what actually happens in the immediate aftermath, over the first weeks and months, and into the first year or two. This is the period where the colony looks from the inside completely fine. Nothing dramatic occurs. That is the entire character of this first phase. Oxygen keeps flowing, because the electrolysis units and the atmospheric plant keep running on reactor power, and there is plenty of water to split, and plenty of carbon dioxide in the sky. The water loop keeps closing, catching the same water over and over, sipping from stored ice to make up the small losses. The reactor keeps its steady beat through a dust storm that rolls over the region and dims the solar arrays to almost nothing. Nobody even loses sleep over it, because the reactor was built precisely so that the sky going dark would not matter. In the greenhouses, crops come in on schedule, and the pantry of stored food sits there as a thick, comforting margin. If a harvest fails, there is a warehouse to lean on. The clinic has shelves of medicine. The workshop has bins of spare seals and fittings and filters. If a pump fails this month, a technician pulls a replacement from stock, swaps it in, and the incident becomes a line in a maintenance log rather than a crisis. To sit inside that early calm is to feel almost nothing wrong at all. A sol on Mars runs a little longer than an Earth day, and the colony's rhythm has settled comfortably into it. The soft artificial dawn brought up on the habitat lights, the green smell of the greenhouses on the morning air, the reactor readout sitting reassuringly flat on its screen in the control room. There is a shift in the farm, and a shift in the workshop, and a shift watching the machines that watch the air. Children take lessons in a room whose walls are packed thick with regolith against the radiation. Someone complains, again, about the algae. In the evening, the same handful of faces gather to eat the same familiar food and argue amiably about nothing at all. Once, this cadence was punctuated by the arrival of cargo, a lander every so often dropping out of the sky with mail and parts and small luxuries, a pulse of connection to a home world that still answered. That pulse has stopped now, but its absence does not yet ache, because the pantry is full and the bins are full and the loops are turning, and the human mind adjusts with frightening ease to a quiet it has not yet learned to fear. If you measured the colony's health during this window purely by the question we started with, can these people stay alive? The answer is a confident and genuine yes. They could keep breathing, drinking, and eating like this for a good while on the strength of reserves and recycling alone. This is the submarine phase. Sealed off, self-contained, coasting on what it already carries. A well-run outpost could hold this pattern together for a year, maybe several, with careful rationing and a little luck. And if that were the whole story, the answer to our title would be cheerful and boring. But something is happening underneath all this calm. Something no alarm on any panel is designed to detect. And to see it, you have to look very hard at that word we have used again and again without flinching. Recycling. Here is the quiet, load-bearing truth of the entire episode, stated as plainly as it can be. A loop is not a source. Recycling does not create anything. It only rearranges what is already present, again and again, capturing and reusing the same finite stock of atoms, and no loop is ever perfect. That celebrated 98% water recovery is a triumph, precisely because it is not 100%, which means that with every single cycle, a sliver of water is lost for good, escaped as vapor, trapped in a brine, bound up in waste the system cannot quite reach. 2% of a large number, cycle after cycle after cycle, is a slow, patient bleed. The colony is a bucket, and every one of its beautiful closed loops has a pinhole in the bottom. For a long while, that does not seem to matter, because the buried ice can top up the water and the atmosphere can top up the oxygen. The raw materials are genuinely abundant. Mars is not going to run out of carbon dioxide or ice on any human timescale. And this is exactly the seductive half-truth that makes a Mars colony sound self-sufficient when it is not. Having the raw material is not the same as having what you need. The colony does not survive because Mars contains water and carbon dioxide. It survives because it possesses working machines that can convert that water and that carbon dioxide into breathable air and drinkable water, and those machines are not made of Martian ice. They are made of membranes and catalysts and precision-machined metal and circuit boards, every one of which was manufactured on Earth, and every one of which is, at this very moment, beginning to age. Look again at what is actually keeping these 250 people alive through this calm early stretch, and you notice something unsettling hiding in plain sight. It is not the ice in the ground. It is not the gas in the sky. It is not even, in the end, the reserves in the warehouse, because reserves are, by definition, a quantity that only ever goes down. What is keeping everyone alive is a set of machines, the electrolysis stacks, the pumps, the scrubbers, the reactor, the grow lights, the printers, and every one of those machines has a lifespan. They wear, they clog, they corrode, they fail. And when a part fails, the colonists reach into a bin of spares that also, quietly, only ever goes down, and can never, on the day the signal died, be restocked from the sky. Which means the colony is not, in truth, counting down its oxygen. It has effectively unlimited oxygen. It is not counting down its water. There is buried ice enough for millennia to come. What the colony is actually counting down from the very second that last empty contact window closed is the working lifespan of the machinery that stands between 250 warm, arguing, complaining, hopeful human beings and a planet that is trying, patiently and without malice, to freeze and suffocate every one of them. That is the real clock, and it is not the one hanging on the wall of the command module ticking off the souls. It is a whole bank of hidden clocks, one for every filter and seal and pump and stack and circuit board in the settlement, each running down at its own quiet pace. Most of them started long before Earth ever went silent, and not one of them showing its face on any screen the crew knows to watch. In the calm of that first year, nobody is looking at those clocks. They are too busy being alive. They are about to start failing, and when they do, they will not fail, one at a time. The end of the calm does not announce itself. There is no siren, no flashing panel, no dramatic countdown on a screen. What actually happens is that a pump in the water plant, one of dozens, starts to make a sound it did not use to make a faint, dry whisper under its hum, the sound of a seal that has spent a few too many months squeezing against a spinning shaft. A technician hears it, frowns, walks to the spares bin, pulls out a replacement seal, and swaps it in over a lunch break. The plant runs sweet and quiet again. The incident becomes 3 lines in a maintenance log, and nobody notices that the colony just spent something it can never earn back. That is the shape of what comes after the calm. Not catastrophe, but attrition. Not one great blow, but 10,000 tiny withdrawals from accounts that no longer take deposits. To understand why a settlement this capable is nonetheless in serious trouble, we have to look closely at the difference between the 2 verbs that decide its fate. The colony is extraordinarily good at one of them, and almost helpless at the other. It can recycle, it cannot replace. Recycling, as we established, reclaims molecules. It catches the same water, the same oxygen, the same carbon, and runs them around the loop again. But a machine is not a molecule. When a seal wears through, no recycling loop hands you a new seal. When a filter clogs, no amount of clever chemistry unclogs it into a fresh one. The colony's magnificent closed loops keep the atoms of life circulating, but the loops themselves are built from parts that sit outside every loop, parts that only ever degrade, and that the settlement, on the day the signal died, lost all ability to obtain. So while the atoms cycle endlessly, the machinery that cycles them runs down one component at a time, and each component has its own private clock, ticking at its own speed. Most of them started long before Earth fell silent. Let us walk the clocks, because there is not one of them. There are whole banks of them, and they are running at once. Begin with the simplest and most relentless, the consumables. These are the parts of the life support system that are used up by design, that were always meant to be thrown out and replaced. The water plant that achieves that celebrated recovery does not do it by magic. It does it with filter beds, with membranes, with resin cartridges, and with pre-treatment chemicals that have to be added to the wastewater before it can be processed at all real substances, consumed in every cycle, that on the space station are simply reordered from Earth whenever they run low. The air system leans on scrubber material and desiccants that saturate and must be regenerated or renewed. Every one of these is a thing that gets spent and does not come back on its own. The colony has a warehouse of them, yes, but a warehouse is a fixed number, and the loops draw on it every single day. Here is the cruel twist buried inside the consumables clock, and it is worth slowing down for. The colony's survival is usually described in terms of those beautiful efficiency figures: recover 98% of the water, scrub nearly all of the carbon dioxide, but those percentages are not laws of nature. They are the performance of specific hardware fed with specific consumables. As the pre-treatment chemicals run thin and the technicians start rationing them, the recovery rate does not stay at 98% out of politeness. It sags, maybe to 90, maybe to 80, and every point it sags, the pinhole in the bucket widens, and the settlement has to mine and melt and purify more raw ice, using more reactor power and more machinery, just to stand still. The efficiency the whole plan depends on is not a permanent gift. It is a rental, paid for in supplies that are no longer being manufactured anywhere in the universe that these people can reach. Now the second bank of clocks. Mechanical wear. Anything that moves wears. Pumps have seals and bearings and impellers. Compressors have pistons and valves. Fans have spindles. The atmospheric plant that pulls oxygen from the Martian sky runs a compressor hard, continuously, against a planet's worth of thin cold gas. The electrolysis units that split water carry solid oxide stacks. And even in the celebrated MOXIE demonstration, those stacks showed a small, steady creep in their internal resistance over time, the quiet fingerprint of a component aging under load. Nothing on Mars runs gently. Everything runs against extreme cold, against abrasive dust finer than talcum that works its way into every joint, against pressure differences that never let up. Moving parts in that environment do not last the way a household appliance lasts in a warm, dry kitchen. They grind themselves toward failure on a schedule written into their materials, and when they fail, you reach into the bin that only empties, and you spend another irreplaceable part to buy another stretch of time. The third bank is subtler and, in the long run, more frightening than the first two. Electronics. Every machine in the settlement is governed by a brain, a controller stuffed with circuit boards, processors, and sensors. The reactor is regulated by electronics. The water plant decides what to do based on electronics. The greenhouse lights, the air scrubbers, the pressure valves, the temperature controllers, all of them are only as alive as the small silicon mines that run them. And silicon does not last forever, least of all on Mars. That same thin atmosphere and absent magnetic field that forced the colonists underground also let high-energy radiation sleet through the electronics on the surface, and, to a lesser degree, everywhere else. Radiation degrades semiconductors. It flips bits, corrupts memory, and slowly poisons the delicate junctions that make a chip. Sensors drift out of calibration and start lying to the systems that trust them. A controller does not have to explode to kill the machine it runs, it only has to become confused. And here the colony hits the hardest wall of all, because a settlement of 250 people does not have a semiconductor foundry. Making a modern microchip requires an industrial cathedral, ultra-pure materials, exotic chemicals, clean rooms, and machines that themselves took a global economy to build. You can machine a new bracket. You cannot machine a new microprocessor. When the last spare controller for a critical system dies, that system does not get a replacement brain. It gets a funeral. Now for a clock hiding inside the one system we were proudest of. Earlier we called air the colony's strongest single card, and in one sense that was true. The colony can make oxygen without limit, but breathable air is not oxygen. This is the subtlety the cheerful version always skips. If you filled the habitat with pure oxygen at the pressure your lungs actually want, you would be living inside a bomb, because pure oxygen turns the smallest spark into a catastrophe, and over time is toxic to the body besides. The air you are breathing right now is mostly not oxygen at all. It is roughly 4/5 nitrogen, an inert gas that does nothing for your metabolism and exists in the mix purely to dilute the oxygen down to something safe. Call it the padding in the air, the quiet, unglamorous filler that no one ever thinks about, and that every pressurized room absolutely requires. The colony needs that padding too, and here Mars turns miserly. The Martian atmosphere is about 95% carbon dioxide and holds only a few percent nitrogen and a little argon between them. To pull enough buffer gas out of that thin, stingy sky, the colony must grind enormous volumes of atmosphere through yet another power-hungry plant, with yet another bank of pumps and filters. And it must keep doing it, because every time an airlock cycles a person out to the surface, and every time the habitat leaks its slow, invisible leak, buffer gas escapes and is gone. The colony can always make more oxygen. What it quietly bleeds, cycle after airlock cycle, is the inert padding that makes the oxygen safe to breathe one more consumable, drawn from one more machine on one more clock. And there is a bank of clocks governing something even more fundamental than air, something so constant the colonists stop hearing it: temperature. The habitat is a warm island in a killing cold, and holding that warmth is only half the problem. The obvious half is heat. Outside sits at around -60 degrees Celsius on a gentle day, and the habitat must be kept warm through walls that are forever trying to leak that warmth away into the dark. But the stranger, less intuitive half is the opposite. The reactor, the smelters, the electronics, the lights, the bodies of 250 living people, all of it pours out waste heat, constantly, and in a sealed, insulated box that heat has nowhere to go. The colony must actively throw its own warmth away or slowly cook inside its own shelter. On Earth, the air and the oceans carry our waste heat off without our noticing. On Mars, the atmosphere is far too thin to do the job, so the only way to dump heat is to pump it through coolant loops out to great radiator panels and let it bleed into space as infrared glow. Think of it as a fever the habitat must throw away, hour after hour, forever. And that whole system, the coolant, the pumps, the valves, the vast delicate radiators exposed to the abrasive dust and the temperature swings, is one more machine that wears, leaks, clogs, and fails. Let the heating falter and the habitat freezes. Let the heat rejection falter and it broils. Both directions are lethal. Both depend on pumps and working fluid and controllers that only degrade. And both were once quietly guaranteed by parts in a bin that no longer refills. There is one more environmental clock, and unlike the others, it does not tick inside a single machine, it speeds up all of them at once. It is dust. Martian dust is not the coarse sand of a beach. It is a fine grey powder, ground over eons into particles so small they behave almost like smoke, statically charged and utterly pervasive. It hangs in the thin air, it settles on every surface, and it works its way through every seam and seal the colonists ever cut. Think of it as a tax the planet never stops collecting, levied on every exposed machine the settlement owns. It coats the solar arrays and throttles their output, so that the daylight power the colony leans on quietly dwindles between cleanings. It settles on the great thermal radiators and dulls their ability to shed heat, nudging the whole habitat toward the slow overheating we just described. It infiltrates bearings and hinges and airlock seals, accelerating the mechanical wear already grinding away, turning a part that might have lasted years into one that gives out in months. Every machine that touches the outside, every rover, every mining rig, every antenna motor ages faster because of it. And every hour spent brushing it off panels and filters and seals is an hour of irreplaceable human labour spent not on building the future, but on merely holding the present in place. And Martian dust carries a second, quieter menace that the cheerful version never mentions. It is chemically hostile. The Martian soil is laced with perchlorates, reactive salts that are toxic to the human body, capable of disrupting the thyroid and dangerous to breathe. Every time a colonist comes in from the surface, that fine toxic powder rides in on the suit, and the settlement must fight a constant, the meticulous battle to keep it out of the air, the people breathe and the water, the greenhouses drink. It means airlocks that scrub and filter obsessively on filters that are themselves consumables on their own clock. It means that the very regolith the colony wants to mine for water and metal has to be cleansed of poison before a single crop can safely touch it. The dust does not kill quickly or dramatically. It does something worse for a settlement trying to last. It makes everything harder everywhere all the time, a permanent friction dragging on every other system, speeding every countdown, and demanding a share of scarce human attention that a short-handed colony can never quite afford. Stack these banks of clocks together: consumables, mechanical wear, electronics, buffer gas, thermal control, and the ever-present grind of dust, and you begin to see the settlement not as a fortress, but as a vast assembly of countdowns, each one independent, each one indifferent to the others, none of them visible on a single dashboard. The command module has a clock on its wall counting souls since landing. That is the wrong clock. The clocks that matter are scattered through every module, one for every membrane and bearing and board and radiator, and the crew cannot read most of them until they run out. And now for the property that turns a manageable problem into a lethal one. These systems are not independent of each other, even though their clocks are. They are woven together into a single fabric, and pulling any one thread slackens the whole cloth. This is the interdependence trap, and it is the beating danger at the center of it all. Cut one strand and the tension redistributes across every other strand, and the whole structure sags toward collapse. Consider what the greenhouse actually needs in order to grow a single leaf of lettuce. It needs light, which means electricity, which means the reactor and its controllers and its cooling. It needs a warm pressurized volume, which means intact seals, buffer gas at the right pressure, and a working thermal control system pumping heat where it belongs. It needs water, which means the water plant, its pumps, its filters, its consumables. It needs carbon dioxide at the right concentration, which means the air system is balancing the atmosphere correctly. It needs nutrients dissolved in that water, which means the nutrient recovery system is turning waste back into fertilizer. Every one of those is a separate machine with its own bank of clocks. The lettuce leaf sits at the far end of a chain of perhaps a dozen dependencies, and if any single link in that chain fails, the leaf never grows. The greenhouse is not a source of food so much as it is a customer of every other system in the colony at once. Now widen the view, because every major system is like this. The water plant is a customer of the power system and the thermal system and the electronics. The air plant is a customer of the water plant, because it splits water for oxygen and of the power system, and of its own controllers. The reactor itself, the supposed bedrock, is a customer too. It needs its coolant pumps and its control electronics and its heat radiators to keep working, and those wear and degrade like everything else. There is no truly independent system anywhere in the settlement. Everything is drinking from everything else, and that means failures do not stay politely in their own lane. They cascade. Picture a single, ordinary fault, not a meteorite, not a hull breach, nothing cinematic, just a power converter that quietly dies one night, the kind of unglamorous box that turns electricity from one form into another, on its own replaceable. But while it is down, a section of the habitat loses power. That means a set of pumps stops. That means a heat exchanger stops moving warmth, and one module begins to cool toward the killing temperatures outside. As it cools, water somewhere begins to freeze in a line it was never meant to freeze in, and the ice cracks a fitting. Meanwhile, the greenhouse in that section, suddenly cold and dark, loses a crop that took months to mature and cannot be unlost. The technicians fix the converter within a day they had a spare, but the colony still comes out the far side of that single, minor, fully repaired fault with a cracked fitting, a dead harvest, and a fresh dent in 3 separate supply reserves. One failure, one afternoon, and the damage spread sideways through the web into systems that had nothing to do with the original fault. This is what it means for systems to be interconnected. It is not that any one clock runs fast. It is that when one runs out, it yanks on all the others. We have been talking about metal and silicon, but the colony is also a biological system, and biology keeps its own merciless clocks, 2 of which now demand attention. The first is medicine. Our settlement has a clinic, and the clinic has shelves, antibiotics, painkillers, anesthetics, drugs for chronic conditions, sterile supplies for surgery. On the day the signal died, Those shelves represented the entire pharmaceutical capacity of the human presence on Mars, and from that day they could only shrink. Medicines expire. The chemistry that makes a pill effective degrades over months and years, whether or not anyone uses it, until a dose that once cured becomes a dose that does nothing. And a colony of 250 people cannot manufacture more. A pharmaceutical industry is not a cabinet. It is a sprawling web of chemical synthesis, purification, and quality control that took Earth centuries and an entire scientific civilization to assemble. So the medical clock runs, and it runs toward a specific, quiet horror. The day a colonist develops an infection that a single course of antibiotics would have cured for free on Earth, and there is no working course left to give. A person who would have lived becomes a person who does not because Mars is especially deadly that day, but because a particular molecule aged out of existence and could not be remade. The same logic hangs over every treatable condition, every surgery that needs anesthesia, every chronic illness that needs a daily drug. The clinic does not run out of care all at once. It runs out one capability at a time, in an order no one can fully predict. And beneath the acute medical clock runs a slower, grinding biological one that touches everyone. Mars pulls on the human body at roughly a third of Earth's gravity, and the body, sensing it needs less strength, quietly gives strength away, thinning bone, wasting muscle across years of residence. The radiation that soaks the surface raises the lifetime odds of cancer with every sol of exposure, a bill that comes due slowly and cannot be recalled. These are not emergencies. IDB4B. They are trends, and they mean that even a colonist who never catches an infection is aging inside an environment gently hostile to the long-term function of the human animal, in a settlement whose ability to treat the consequences is itself running down. The second biological clock is food, and this is the one where the cheerful version of the Mars story is most tempting and most wrong. Yes, the greenhouses grow crops. Yes, astronauts have grown and eaten fresh vegetables in orbit. But look hard at what has actually been demonstrated versus what is quietly assumed. What has been grown off-world, so far, is essentially garnish lettuce, radishes, a few peppers. Fresh, morale-lifting, genuinely valuable, and nowhere near a diet. What keeps a human being alive is not salad. It is calories, mostly from staple crops like wheat, potatoes, soybeans, and rice, plus complete protein and a long list of vitamins and minerals in the right amounts. Growing those staples at the scale and reliability needed to feed a town, inside sealed artificial rooms with no failed harvest ever backstopped by a shipment from outside, is something no one has ever actually proven can be done indefinitely. It is plausible. It is not demonstrated. And the gap between plausible and demonstrated is exactly the gap a colony cut off from Earth falls into. The food clock has hidden hands too. A sealed agricultural system does not grow food out of nothing. It needs nutrients, nitrogen, phosphorus, potassium, and more dissolved and delivered to the roots. On Earth, those come from a vast fertilizer industry. In the colony, they must be recovered, relentlessly, from the settlement's own waste, closing yet another loop with yet another pinhole in it. Every leak in the nutrient loop is a slow drain on the colony's ability to grow the next crop, and the makeup has to come from somewhere, from stored fertilizer that only depletes, or from chemistry the colony may not be able to run. Then there are the vitamins that plants make poorly or not at all. Vitamin B12, for instance, is notoriously hard to get from a purely plant-based system, which is why the stored supplements in the warehouse matter, and those supplements, like the medicines beside them, expire. And a greenhouse packed with genetically similar plants is a standing invitation to disease. Introduce one blight, one mold, one pest into that warm, wet, crowded environment, and with no fresh seed stock and no resupply of the chemicals to fight it, a single infection can sweep the racks and erase a food source in weeks. So the food story, examined honestly, is not the colonists grow their own food and are therefore fine. It is the colonists grow some food, backstopped by expiring reserves, inside a fragile system that depends on nutrient loops that leak, seed stocks that dwindle, and a disease-free environment that cannot be guaranteed. Growing some crops is simply not the same thing as owning a complete, resilient, indefinitely renewable food supply. The first is demonstrated, the second is the actual requirement. And once again, the settlement is living in the space between them, and there is one more system keeping the colony alive that has no filter, no membrane, and no spare in any bin the colony itself. As a society of human minds, this clock is the easiest to forget and among the hardest to reset, because it runs not in the machinery but in the people who keep the machinery alive. 250 human beings are now sealed together for the rest of their lives on a cold world with no exit, no leave, no home to go back to, and no news from anyone beyond their own corridors. Every one of them has just watched Earth, every friend, every relative, every place they came from go silent forever, and there is no grief counsellor arriving on the next flight, because there is no next flight. The mind is a system too, and it fails in its own ways. Despair, exhaustion, the slow corrosion of purpose in people who never quite chose this fate, and the children who certainly did not. Add to that the brute mechanics of governance in a town this size. Who leads? Who decides how the last of a scarce medicine is spent, or which greenhouse gets the power when there is not enough for both? In a population this small, a single bitter schism, a loss of trust, a struggle over authority, does not stay a private unhappiness. It becomes an existential threat, because every survival system depends on people cooperating to maintain it. A water plant does not care about morale, but it stops running all the same if the two people who know how to service it will no longer work in the same room. The psychiatric medicines that might steady all this are on the same expiring shelf as the antibiotics. The colony can survive the failure of a pump. Whether it can survive the failure of its own cohesion is a question no engineering diagram can answer, and it is running the whole time, underneath everything else. Now assemble the whole picture of what happens next. The colony is not running out of oxygen, it can make oxygen. It is not running out of water, it can recycle water and mine ice. It is not, for a good while, running out of calories, it has greenhouses and a warehouse. What it is running out of, on a dozen different independent schedules, is working machinery and irreplaceable consumables and buffer gas and unexpired medicine and complete nutrition, and quietest of all, social cohesion, all of it lashed together into a single web, where the failure of one strand tugs at every other. And crucially, none of these clocks, not the seals, not the stacks, not the circuit boards, not the radiators, not the dust that fouls them, not the pre-treatment chemicals, not the antibiotics, not the fertilizer, not the fraying nerves of the people is stopped, slowed, or even slightly eased by the fact that Mars is drowning in raw materials. This is the point that has to land before we can go any further, because it is the hinge on which the entire survival question turns. There is buried ice enough for 100 civilizations. There is carbon dioxide without limit in the sky. There are metals and silicon and every common element locked into the regolith under the colonists' boots. Mars is not a poor planet. It is a warehouse of raw stock the size of a world, and not one atom of that abundance can by itself become a replacement seal, a fresh membrane, a working microchip, a dose of antibiotic, a tank of buffer gas, or a complete meal. Raw material is not the same as the thing you need. Between the ice in the ground and the water in the pipe stands a machine. Between the ore in the rock and the circuit in the controller stands an entire industry. The colony is surrounded by everything it could ever want and can convert almost none of it, because conversion is not a resource. It is a capability, and capability is precisely what the settlement is watching drain away, one failed component at a time, which reframes the whole problem and points it straight at the next phase. Survival, it turns out, was never going to be decided by how much ice, or gas, or ore the colonists could reach. It was going to be decided by a single, far harder question. Can this settlement of 250 people stop merely repairing its dying machines from a finite bin of Earth-made spares, and start actually making new ones, new parts, new consumables, new medicines, new complete food out of the raw Martian world around them? Because if they can, the clocks can be reset, and the colony has a future. And if they cannot, then every countdown we have just walked through is not a problem to be solved. It is a sentence being slowly read aloud. The submarine coasts beautifully right up until the moment it needs a part it did not bring. What would it actually take to build that part on Mars? That is where we go next. By the time the colony truly understands its situation, it has already been living the answer for months without naming it. The technicians have noticed that the spares bins are thinning faster than anyone modelled. The chief engineer has started keeping a private ledger not of oxygen or water, which are fine, but of seals, of pump bearings, of controller boards, of the pre-treatment chemicals that make the water plant work. And somewhere in that ledger, a realization crystallizes that changes the entire character of the settlement's project. Repairing the machines is not enough. Repairing only spends the bin. To have a future, the colony has to stop taking parts out of a box that Earth once filled and start making parts out of the planet it is standing on. That sentence sounds simple. It is the hardest sentence in this whole story, because there is a gulf between two capabilities that look almost identical from a distance and are worlds apart up close. The first is repair, taking a broken machine and restoring it using parts you already have. The second is manufacture, taking raw rock, ice, and air, and producing those parts in the first place. The colony arrived on Mars extremely good at the first, and almost entirely incapable of the second. Every settlement that has ever been imagined can fix things. Almost none could build the things it fixes with, from scratch. And the distance between fixing and building is exactly the distance between an outpost that is slowly dying and a civilization that could live forever. Let us be scrupulously fair to Mars first, because the raw material really is there, in quantities that beggar belief, and it would be dishonest to pretend otherwise. We have already established the water ice, mapped and confirmed across the mid-latitudes, enough to supply a city for geological ages. But the generosity does not stop at ice. The atmosphere, that thin carbon dioxide sky, is a chemical feedstock. And it is worth being concrete about how, because this is the one place the colony's chemistry genuinely delivers. Take carbon dioxide from the air and hydrogen split from water, warm them together over the right catalyst, and a well-understood industrial reaction more than a century old, run in factories on Earth long before anyone dreamed of Mars, yields methane and more water. That methane is rocket fuel, and it is also the first rung of a plastics industry, because the same carbon that makes methane can be built up into the polymers that become pipes, insulation, and printer stock. So from nothing but air, water, and power, the colony can, in principle, make fuel, water, and the raw carbon backbone of plastic. The regolith underfoot, the loose broken rock covering the entire planet, carries the rest. It is not inert dirt. It is ore, rich in iron, in silicon, in aluminum, in magnesium, in titanium, and in oxygen bound chemically into the minerals themselves. In principle, a colonist standing on the Martian surface is standing on all the elements needed to make metal beams, glass panes, ceramic tiles, silicon wafers, and concrete-like building blocks. Mars is not a desert in the sense of lacking materials. It is closer to an unopened warehouse the size of a world, every shelf stocked, every crate sealed. And here is where the seduction lives, the exact place where the cheerful version of this story quietly lies to you. It points at that stocked warehouse and says, look, the colony has everything it needs, but having the ore is not having the beam. Having the silicon in the rock is not having the wafer, let alone the chip printed onto the wafer. Between the raw element and the finished part stands a process, a chain of extraction, refinement, purification, forming, and assembly, and that process is not a resource you can dig up. It is a capability you have to build, maintain, power, and staff. The warehouse is full. The colony's problem was never the contents of the warehouse. It is that Earth kept the keys, the forklifts, the loading dock, and every worker who knew how to turn a crate of ore into a working pump. Those did not come in the last cargo. Those were the whole of Earth, standing invisibly behind the last cargo. So let us actually try to build a single replacement part on Mars and watch how deep the hole goes. Start with something that sounds almost trivial. The colony needs a new metal bracket, a simple structural piece, and the old one has cracked. Even this, the easy case, is not free. To make a metal part from Martian rock, you must first mine the regolith, which means machines that dig, and those machines have motors and bearings and cutting edges that wear against abrasive stone and must themselves be maintained. Then you must extract the metal from the ore, which is not a matter of melting rock in a pot. Iron and aluminum are locked into minerals chemically, and prying them loose takes energy-hungry processes, high temperatures, reactive chemicals, careful control, every step of which needs equipment, power, and people who understand metallurgy. Then you must refine the crude metal to something useful, form it into shape, and finish it to the tolerances the machine requires. The colony does, in fact, have a partial answer to the very last step, three-dimensional printers, and it is worth being precise about what those printers can genuinely do, because this is one of the places the fantasy runs furthest ahead of the facts. Off-world manufacturing is real, and it is a genuine marvel, but look hard at where it actually stands. Astronauts have been printing plastic parts on the space station since 2014, and only in the summer of 2024 did the first metal part ever get printed in space at all. A small stainless steel sample, painstakingly coaxed out of a laser-melted wire over months of careful operation, then shipped back to Earth so that scientists could study whether it came out sound. That is the true frontier. Not a factory humming out engine parts, but a single small test shape, made once, as a proof that the thing can be done at all. This is the honest baseline. The colony's printers, descendants of these machines, can make brackets, housings, simple tools and structural pieces from metal and plastic feedstock. That is not nothing. It might on its own buy the settlement years because a great many failures are mechanical and simple, and a workshop that can print a new bracket or machine. A new bearing is a workshop that can keep a lot of machines limping forward. But before we lean too hard on those printers, notice what they eat. A printer does not conjure a part out of the air. It lays down feedstock, spooled metal wire, metal powder, polymer filament melting, and stacking material that had to come from somewhere. And in the beginning, that somewhere is the same warehouse as everything else. The printer feedstock sits in the bin, and the bin only empties. A printer is a mouth, not a cornucopia. Feed it, and it makes wonders. Starve it, and it is an expensive paperweight. So the settlement's celebrated ability to just print a replacement is, at first, not a way out of the supply problem at all. It is merely a different way of spending the same finite hoard, converting bars of imported metal into brackets until the bars run out. Real independence at the printer means something far harder than owning the printer. It means making the feedstock to refining Martian iron into wire of the right alloy and purity, building polymer filament out of that carbon pulled from the atmosphere. Until the colony can feed its own printers from the planet, the printers are not a source. They are just one more shelf in the emptying warehouse, and the day the last spool runs dry, the workshop that was supposed to save the colony goes as quiet as everything else. Now push the printer to make the part that actually failed, and watch it stop dead, because the parts that most often kill a life support system are not simple lumps of metal. They are the clever parts. The membrane in the water plant, a sheet of polymer engineered at the molecular level to let water through and block contaminants. A printer that lays down metal wire cannot make that. The catalyst that makes a chemical reaction run at all, a precisely structured material that a whole branch of industrial chemistry exists to produce, you cannot print it. The seal, which sounds humble but is a specific formulation of rubber or polymer, chosen to stay flexible at Martian cold and survive contact with specific fluids. Its recipe is an industry unto itself. And above all, the electronics, the controller boards, the processors, the sensors. No printer anywhere, on Earth or off it, prints a microchip. A modern microchip is arguably the most complicated object our species makes, the product of a global supply chain of ultra-pure silicon, exotic gases, photographic light-etching machines that themselves take entire nations to build, and clean rooms cleaner than any operating theatre. The number of distinct, specialized steps hidden inside one small circuit board exceeds anything a town of 250 people could ever hope to reproduce. You can print the housing that holds the electronics. You cannot print the electronics. This is the true shape of the manufacturing problem, and it deserves a clean image to hold it by. Think of everything the colony needs to make as a pyramid. At the broad, forgiving base sit the simple parts. Brackets, beams, tools, tanks, bricks, Structural pieces, things that need shape more than sophistication. A colony with printers, machine tools, a metal supply, and skilled hands can hold this base of the pyramid, and holding it matters enormously. One tier up sit the harder items: seals, gaskets, wiring, glass, ceramics, basic chemicals, things that need real material science and dedicated processes, achievable in principle, but only if the colony has built the specific industries to make them. Higher still sit the specialized components: membranes, catalysts, pharmaceuticals, complex alloys, precision bearings, each one the fruit of a deep, narrow industry that took Earth generations to grow. And at the very tip of the pyramid, tiny and glittering and utterly out of reach, sit the microchips and advanced electronics that quietly govern every system the colonists depend on. The colony can build the base of the pyramid. It can fight its way part way up the second tier if it is brilliant and lucky. And the top of the pyramid, the part that runs everything else, it almost certainly cannot build at all. The tragedy is that a machine is only as alive as its highest tier part. A water plant with a perfect printed housing and a perfect machine shaft is still dead if its controller board dies, and there is no new board and no way to make one, which exposes the deepest trap in the entire undertaking, the one that separates a colony that postpones death from a colony that escapes it. To manufacture parts, you need tools, but the tools are themselves machines. The printer has motors and lasers and electronics. The mining robot has bearings and controllers. The metal furnace has heating elements and sensors. The chemical reactor has pumps and valves and, yes, membranes and catalysts of its own. So the machines that make the parts wear out and need parts, and if the colony cannot make the parts for its part-making machines, then its manufacturing capability is not a permanent gift either. It is just one more thing on one more clock. A colony that can print brackets but cannot make a new laser for its printer has not escaped the bin. It has only added the printer to the list of things in the bin. You might think the obvious defense against all this is redundancy. Simply carry backups. 2 water plants instead of 1, a spare reactor, duplicate air systems, so that no single failure is ever fatal, and a dead machine can be swapped out for its twin while the broken one waits for repair. And redundancy is real engineering. Any serious colony would build in a great deal of it, and it genuinely buys safety in the early years. But look closely and you find that redundancy and self-sufficiency are quietly at war with each other, and the colony cannot fully have both. Every backup is not a free insurance policy. It is a second full machine, with its own seals and membranes and boards and consumables, all of which age on the shelf, whether the unit runs or not, and all of which must eventually be maintained and replaced from the same emptying bin. Doubling the machines doubles the parts that will one day need making. It is like trying to protect one failing heart by carrying spare hearts in your chest. Each new heart is another thing that can fail, another thing to feed, another draw on a blood supply that is already running short. So redundancy does not escape the trap. It multiplies the very dependency the colony is straining to shed. And a settlement of 250 people cannot in any case staff, power, and maintain many parallel industrial systems at once. There are not enough hands to run 3 of everything, nor enough reactor watts to keep them all warm, which lays bare the real dilemma the colony is impaled on. Build few systems, and any single failure can be catastrophic, because there is no twin to fall back on. Build many, and you cannot possibly keep them all supplied and repaired forever, so you have simply enlarged the pile of things that will eventually run out. Fragility on one side, unsustainability on the other, and no comfortable resting place between them, only a choice about which way to lean, made over and over as the parts that back up the backups quietly age in the dark. There is a name for the capability that would finally break this whole tangle of traps, and it is the true threshold this story has been walking toward. It is the point at which the colony's industrial base can reproduce itself, where the settlement can make not only the parts for its life support machines, but the parts for the machines that make those parts, and the parts for the machines that make those, all the way around, until the loop closes on the machinery itself the way it already closes on the water and the air. A settlement that reaches that point has done something profound. It has stopped being a consumer of Earth's industry and become a source of its own. It can lose a printer and build a printer. It can lose a furnace and build a furnace. Its clocks can at last be reset from the inside. Below that threshold, every capability is borrowed against a bin that only empties. Above it, the colony is genuinely alive as a civilization, able to bleed and heal, to break and rebuild, indefinitely. No human society has ever had to build that closed industrial loop from 250 people and a warehouse of spares on a planet trying to freeze them, with no chance of help. That is the mountain. The question of survival is really the question of how far up that mountain the colony can climb before its borrowed tools give out. And that phrase, before its borrowed tools give out, hides the cruelest constraint of all, one that has nothing to do with whether a thing is possible, and everything to do with whether it is possible in time. Every industry we have been so calmly listing is not a switch to be flipped, but a construction project of years. A smelter that can pull iron from regolith is not a machine you unbox. It is a furnace that must be designed, built, walled, powered, vented and debugged, and the building of it consumes metal and parts and power the colony would otherwise be spending on staying alive. A chemical works to make its own catalysts, a glass works, a foundry, a plant to spin polymer into printer filament. Each is a multi-year undertaking, and each must be built using the very earth-made tools and spares that are draining away while it is being built. This is the true vice the settlement is caught in, and it is worth naming plainly. There are two clocks running toward each other. One counts down the imported spares and consumables keeping the colony alive today. The other counts up, painfully slowly, toward the day the colony can make those things for itself. Survival depends entirely on which clock reaches its mark first, on whether the settlement can stand up a self-feeding industrial base before the hoard that sustains the effort runs dry. And the terrible asymmetry is that building industry is slow and failure is fast. A furnace takes years to raise. A critical pump takes an afternoon to die. The colony is trying to build a lifeboat out of the timbers of the ship, while the ship is going down beneath it, and the water is rising the whole time. Worse, the effort to escape actively deepens the immediate danger, because the colony has only one pool of hands and must rob one task to feed the other. Put a machinist on building the smelter, and you have taken that machinist off maintaining the machines that are keeping people alive right now. Every hour of skilled labor poured into the future is an hour stolen from the present. It is robbing the watch to build the workshop, and the watch is what stands between the colony and a cascading failure tonight. A settlement that throws itself wholly into industrialization may find that its maintenance slips, its small failures go uncaught, and it dies of a neglected pump long before its glorious new foundry ever pours its first metal. A settlement that plays it safe and keeps every hand on maintenance never builds the foundry at all, and simply dies later instead of sooner. There is no comfortable path between those errors. The colony must gamble a portion of its survival margin on a long bet that may not pay out inside the lifespan of the parts it is gambling with, and it must make that gamble while short-handed, exhausted, and grieving. This is not a problem cleverness dissolves. It is a problem of too few people, too little time, and two clocks running in opposite directions. And even setting the clocks aside, climbing the mountain takes two more things the colony has in strictly limited supply, and both deserve a hard look, because they are where the real ceiling lives. The first is power, and here the reactor we were once so proud of starts to look less like a fortress and more like another hungry mouth. Recall that our settlement runs a little more than a 40 kilowatt class reactor, chosen because studies suggest sustained human operations want at least 100 kilowatts. That budget was sized to keep people alive to run the air plant, the water plant, the lights, the heat, the greenhouses. It was not sized to run a civilization's worth of heavy industry on top of all that. And industry is monstrously power-hungry, melting metal out of ore, driving chemical reactions, running furnaces and mining machines and printers around the clock. These are among the most energy-intensive things a society does. The colony that wants to manufacture its own parts discovers that it must choose, hour by hour, between keeping the greenhouse lit and running the smelter, between warming the habitat and refining a batch of metal. What the foundry consumes, the machines keeping people alive must do without. To do both at once, the colony would need far more power than it has, and here the reactor reveals its own dependency, because a reactor is not eternal either. It needs its coolant pumps and its control electronics and its radiators, all of which wear, and eventually it needs fuel. A colony that cannot refine reactor fuel and cannot rebuild reactor components is a colony whose very heart is, like everything else, running on a clock, a long clock, perhaps, but a clock. The beating heart we admired at the outset turns out to be borrowed too. The second scarce thing is knowledge, and this may be the quietest and most decisive constraint of all. Everything we have discussed, mining, metallurgy, chemistry, electronics, medicine, agriculture, reactor operation, is not a machine. It is an expertise carried in human minds and human hands. And Earth's industrial civilization does not run on a few brilliant generalists. It runs on staggering specialization, millions of people who each know one narrow slice of the whole extraordinarily well, and who together, without any single person understanding it all, keep the entire machine alive. No individual on Earth knows how to make a pencil from raw materials entirely by themselves, let alone a pump or a chip. The knowledge is distributed across a whole species. Our colony has 250 people. It cannot possibly hold in living minds more than a thin sliver of the expertise that Earth took for granted. It has, at best, one metallurgist, a couple of chemists, a handful of engineers, one or two physicians who trained for very different problems than the ones now facing them. Each of those people is a single point of failure for an entire domain of knowledge. If the metallurgist dies, the colony does not just lose a person. It loses metallurgy, the practical, hands-on, hard-won judgment that no textbook fully captures, the knowing by doing that turns theory into a working furnace. This is where population stops being a background number and becomes the ceiling itself. Ask the honest question, how many people would it actually take to hold, all at once, every skill needed to keep this civilization alive and reproducing? And the answer is sobering. Not 250. To staff a mining operation, a metal refinery, a chemical works, a plastics line, a glass works, a foundry, an electronics effort, however crude, a full farm, a hospital capable of surgery and dentistry and childbirth, a reactor crew, a machine shop, and a school to teach the next generation all of it, and to carry a spare of every one of those specialists so that a single death or illness does not erase a whole craft. You are no longer describing a town of hundreds. You are describing something closer to thousands, and by many serious estimates, tens of thousands, before a settlement could truly reproduce the full industrial base that keeps it alive. Our colony of 250 is not a small city that happens to be on Mars. Measured against what genuine independence requires, it is a skeleton crew enough hands to run the machines Earth sent, nowhere near enough to rebuild them. That gap between the population it has and the population true self-sufficiency demands is not a detail. It may be the single most decisive number in the entire story. The colony has libraries, of course vast digital archives holding the sum of human technical knowledge, every textbook, every paper, every schematic, and that matters. But a library is not a mentor. Hearing how to extract titanium from regolith is not the same as being able to do it, any more than owning every cookbook makes you a chef the first time you try. Skills degrade across generations even faster than they degrade within one. The children born on Mars will grow up learning from a shrinking pool of teachers who are themselves further and further from the industrial civilization that trained them. Knowledge that is not used is knowledge that is lost, and a colony, fighting daily to survive, has little slack to keep alive. Expertise it does not yet urgently need right up until the day it needs it, and finds the last person who had it is gone. Preserving the knowledge to rebuild an industrial civilization is not a matter of storage. It is a matter of continuously teaching and practicing, far more than any 250 people can hold, and the smaller and more stressed the population, the more of it slips through their fingers with every passing year. So place the pieces of this whole problem side by side, and the shape of the settlement's real project comes into focus. To climb from an outpost that postpones death to a civilization that escapes it, the colony must, all at once and forever, mine and refine local materials, run the heavy industry that turns those materials into parts, feed its own printers and tools with feedstock it makes itself, manufacture not only the parts but the machines that make the parts, closing the loop on its own tooling, power all of that with far more energy than it was built to generate, including the power to sustain the very reactor that powers it. Hold in living, practicing human minds, a depth of specialized knowledge that on Earth is carried by millions, and that here rests, in each domain, on one or two irreplaceable people among far too few, and do the whole of it faster than its imported spares run out, with a workforce already stretched to its limit, merely staying alive. Each of those is hard. Together they are the single most ambitious thing any human community has ever been asked to attempt, and the colony must attempt it not from a position of strength, but while its spares bins empty, its consumables dwindle, its medicines expire, and its clocks tick down all around it. None of this means the colony is doomed. That is the crucial thing to hold on to as we move toward the final reckoning. A settlement that is large enough, well-stocked enough, well-powered enough, and deliberately designed from the beginning to build this closed industrial loop could genuinely climb the pyramid, tier by tier, faster than its bins run dry. It could reach the point where it makes its own seals, its own glass, its own simple chemicals, its own structural metal and its own printer feedstock, and resets those clocks one by one. Whether it can reach high enough, whether it can ever conquer the glittering tip of the pyramid, the electronics and the specialized components that govern everything, is the question on which its entire future balances. And that question does not have a single answer. It has a range of answers, one for each kind of colony, each level of preparation, each degree of size and power and foresight. Which is exactly where we must go to finish this. We have watched the reserves that buy the first months. We have watched the clocks that measure the years. We have watched the industrial mountain that would have to be climbed to reach the decades and beyond. Now we can finally put a number, or rather, a set of conditional numbers on the whole thing, and identify the precise threshold that separates a colony, merely delaying its death from one capable of handing life to a generation that will never see Earth at all. Because the settlement we are about to discover does not die when its last shipment is consumed. It dies at a far stranger and more specific moment, the moment it meets the first essential thing its small world cannot make. What that thing is likely to be, and what it would truly take to never meet it, is the final question. Somewhere in the middle years of the silence, on an ordinary evening, a colonist stands at a window looking out at the rust-coloured plain and does a small, quiet piece of arithmetic that no one asked for. Not oxygen, not water, not calories. Those she knows are fine. Those were always going to be fine. What she counts instead is boards. Controller boards, the small green rectangles of etched silicon and solder that sit inside every machine and tell it what to do. She counts how many working spares are left in the sealed cabinet, and she counts how fast, on average, they have been failing. And she divides one number by the other, and she gets a figure in years that she does not say out loud to anyone. Then she goes to dinner, because it is her turn to cook, and the arithmetic waits, patient as the planet. This is how the answer to our question actually arrives. Not as a siren, as arithmetic, done quietly, by someone who has understood the shape of the thing. So let us do the arithmetic honestly now, out loud, and finally answer how long a Mars colony could survive after Earth went silent, with the one crucial caveat this whole story has been building toward. There is no single number. Anyone who gives you a single number is selling you a story, not a truth. The honest answer is a range, and where a given colony lands inside that range depends entirely on what kind of colony it is, how many people, how much stored, how much power, how deep its capacity to repair, and above all, how much of Earth's hidden industry it can rebuild for itself. The number is not a fact about Mars, it is a fact about the colony. So here is the range, in 4 honest tiers. The first tier is survival for months, and it belongs to the weakest kind of settlement, an early outpost. A foothold of a few dozen people living mostly on what was shipped to them, with thin reserves and little real local production. For a colony like that, the silence is close to a death sentence on a short fuse. It coasts on stored food and stored parts, and when a critical machine fails and there is no spare and no way to make one, it is over not in a blaze, but in a slow closing down, system by system, over months. This is the outpost that mistook being resupplied for being alive. When the resupply stops, so before long does it. The second tier is survival for years, and it belongs to a settlement like the reference colony we have followed 250 people, buried and shielded, nuclear-powered, running the best closed loops humanity has built, with greenhouses and a warehouse of spares and medicine and seed. This colony does not die in months. Its air holds, its water holds, its recycling is genuinely superb, and its reserves are deep. It survives the first failures because it has spares, and it survives the first bad harvest because it has stored food. But it is living this entire time off a bin that only empties and loops that only leak. Its survival in this tier is measured in the lifespan of its irreplaceable parts and its expiring supplies. A colony this good, coasting on reserves and recycling and rationing, buys itself years a genuinely impressive stretch. Long enough to raise children, long enough to hope, but it is postponement, not escape. The clocks are all still running. It is buying time, and time is not the same as a future. The third tier is survival for decades, and this is where the colony stops merely coasting and starts fighting back against the clocks. To reach it, the settlement must do what we traced earlier: refine local material, run real industry, feed its own tools, and manufacture its own replacement parts, at least the parts at the broad, forgiving base of the pyramid. A colony that can print and machine its own brackets and bearings and tanks and structural metal, that can make its own glass and simple chemicals, reset some of its clocks from the inside. Every seal it can remanufacture, every mechanical part it can rebuild, is a countdown restarted rather than a countdown expiring. This colony can absorb mechanical and structural failures more or less indefinitely because it can make the mechanical and structural parts. It has climbed the mountain partway, and partway is a very long way. Decades are now on the table, perhaps generations, because the colony is no longer only spending. It is, in real domains, producing. But notice what still isn't solved even here, because this is the hinge on which the entire fate of the settlement turns. Climbing partway up the pyramid, buys the base tiers and leaves the glittering tip untouched. The colony can make its brackets. It still cannot make its microchips. It can machine a shaft. It cannot synthesize a catalyst, or a membrane, or an antibiotic, or grow a complete and resilient diet with no failed harvest ever backstopped from outside. And a machine dies with the least replaceable part inside it. So the colony in the third tier survives for decades. Yes, but it survives while a small number of very specific clocks keep ticking down beneath everything it has built. Clocks it cannot reset no matter how hard it works, because resetting them would require industries it has not been able to reproduce. It is a colony that has escaped almost every way of dying except the ones that matter most. It is worth pausing to watch that third-tier colony actually live out its decades, because the shape of it is not what the word survival usually conjures, and seeing it clearly is the whole point. Picture the settlement 20 years into the silence. By every visible measure, it is thriving. It has raised its foundry and its glassworks. It mines its own ice and its own ore. It prints its own brackets from wire it drew from Martian iron. It has patched, rebuilt, and improvised its way through 1,000 mechanical failures that would have ended a lesser outpost. Walk its corridors, and you would call it a success. But go down to the sealed cabinet where the controller boards are kept, and you would find the shelves noticeably emptier than they were, and no way on this entire planet to fill them again. The colony has climbed a stairway with its top steps missing. It has mastered every tier it can reach, and stalled, permanently, at the one tier that governs all the others, and so its long decline is not a matter of running out of metal or air or food. It is a matter of slowly running out of the small silicon mines that let the metal and air and food machines function at all. The colonists watch it happen and understand it completely, which is its own kind of cruelty. They cannibalize. They take the controller from a rover they can live without and transplant it into the water plant they cannot. They strip a dead greenhouse to keep a living one lit. They grow expert at the grim arithmetic of triage, keeping the essential systems breathing by feeding them the organs of the inessential ones, and for a long time, a genuinely long time, it works. But every transplant is a subtraction from a total that never grows, and the range of things the colony can still do shrinks, capability by capability, year by year. The settlement in the third tier does not fail because it was foolish or unlucky. It fails, if it fails, because it built a magnificent body and could never learn to make the one small part that was its nervous system, and a body, however strong, cannot outlive its nerves. Which brings us to the fourth tier. Survival in definitely true independence. A settlement that could, in principle, last as long as any society on Earth, that could carry human life forward across centuries with no home planet behind it at all. And here we have to be completely clear-eyed, because this tier is qualitatively different from the other three. The first three tiers are about staying alive. The fourth is about staying a civilization. To reach it, the colony must cross a specific threshold, the one we reached earlier, where its industrial base can reproduce itself completely, not only the parts for its life support machines, but the parts for the machines that make those parts, and the tools that make those tools. Closing the loop on the machinery the way the water loop closes on water, all the way up the pyramid to the glittering tip. It must be able to lose a printer and build a printer, lose a chip fabricator and impossibly, but this is the requirement: build the capacity to make chips. And it must close a second loop alongside the industrial one, the biological and human loop. It must reproduce not only its machines but its people, and not only its people but their knowledge, a new generation, healthy, educated, and carrying forward in living minds and practicing hands the full depth of specialized expertise needed to keep the whole system alive. A colony reaches the fourth tier only when it can make everything essential, teach everything essential, and bear and raise the people who will do both after the founders are gone. And that biological loop hides an uncertainty deeper than any machine, one we should be honest enough to state plainly rather than wave away. We do not actually know whether human beings can reproduce successfully on Mars at all. Every child ever conceived, carried, and born in the history of our species has developed in Earth's gravity. Almost nothing is known about carrying a pregnancy to term in a fraction of Earth's gravity, and we simply do not know what 1/3 of Earth's pull does to a developing embryo, to the way a fetus settles into position, to the growth of a skeleton that evolved over hundreds of millions of years under a force that Mars only partly supplies. Layer onto that the radiation, the same sleet of high-energy particles that ages the electronics and raises the colonists' cancer risk, falls on the developing child in the womb and on the reproductive cells that made it, and a developing nervous system is among the most radiation-sensitive things in all of biology. This is not settled science with a reassuring answer. It is an open question with frightening possibilities, and it sits directly athwart the one thing the fourth tier absolutely requires, which is generations. A colony that cannot reliably bring healthy children into the world does not have a multi-generational future, no matter how brilliant its machine shop. And even if the biology cooperates, the numbers bite from the other side. A founding population of a few hundred is a gene pool the size of a puddle. Close a few hundred people off from the rest of humanity forever, and their descendants must marry within that tiny circle, generation after generation, and the known consequences of that, the surfacing of rare inherited diseases, the slow narrowing of the genetic variety that keeps a population healthy and adaptable, are exactly what population biologists spend careers warning about. Serious estimates of the minimum number of people needed to sustain a genetically healthy, isolated human population for the long-term run from the high hundreds into the thousands, and that is before you ask them to also hold every industrial skill. This is why the stored genetic archives, banks of frozen embryos, eggs, sperm, and seed are not a curiosity in the corner of the warehouse, but a central pillar of any real bid for independence, a way to smuggle a wider gene pool across the void in a freezer. And those archives, of course, depend on power and cold and working machinery and expiring supplies, like everything else, which means the colony's biological future is lashed to the very same clocks as its air and its water. No human community has ever done this from scratch. Not because it is forbidden by physics, every element and every principle is available on Mars, but because the thing that would have to be rebuilt is so much larger than it looks. And that is the realization this whole story has been walking toward. The one we sealed away through 3 long chapters so that it would land with its full weight here, at the end. The The colony does not die when it runs out of oxygen. It can make oxygen. It does not die when it runs out of water. It can recycle water and mine ice for 10,000 years. It does not die when the last shipment of food is eaten. It has greenhouses, however imperfect. The colony dies at a stranger, more specific, more revealing moment. It dies when it meets the first essential thing it cannot make, cannot repair, cannot substitute, and cannot live without. That is the true clock. Not the biggest reserve, but the first irreplaceable dependency to run out. The settlement's lifespan is set not by its most abundant resource, but by its most fragile one, the single link in the chain that snaps and cannot be forged again. So what is that link most likely to be? What is the thing that actually ends a Mars colony, not in the fantasy, but in the honest accounting? It is almost certainly not the dramatic thing. It is not a lack of air or water. It is one of the quiet, complicated, manufactured things at the top of the pyramid. And the strongest candidates are worth naming plainly, because naming them is the whole point. It might be electronics. Of everything the colony depends on and cannot make, the microchip is the deepest and the most universal, because it governs everything else. When the last working controller for a critical system fails, and there is no spare, and there is no way in this small world to make a new one, then a system the colonists cannot live without simply goes dark and stays dark. Not because they lacked the metal or the power or the will, but because they lacked one small etched rectangle that took a planet's worth of industry to produce. A colony can be drowning in water, buried in ore, flush with power, and still die because it cannot make a chip. It might be medicine. We have watched the clinic's shelves shrink and expire, and there is a specific quiet horror waiting at the end of that shrinking. The day an ordinary infection meets a colonist, and there is no working antibiotic left to give, and a person who would have lived on Earth for the price of a few pills does not live on Mars, because the molecule that would have saved them aged out of existence and could not be remade. Multiply that across every treatable condition, every surgery needing anesthesia, every chronic illness needing a daily drug, and you have a colony that is medically undressing itself one capability at a time, in an order no one can predict. It might be nutrition, not calories, but completeness. A colony can grow enough food to fill stomachs and still, slowly, starve of the specific things a sealed plant-based system struggles to provide. Certain vitamins, certain nutrients, the vitamin B12 that stored supplements once covered, and that expires like everything else. Deficiency is a patient killer. It does not announce itself. It shows up years in, as failing health across the whole population at once, in a settlement that grew plenty of lettuce and could not close the last few percent of the nutritional loop. It might even be the colonists themselves, a biology that will not carry a healthy child in low gravity, or a gene pool that narrows into sickness, ending the settlement not with the death of the founders, but with the failure of the generation that was supposed to follow them. A colony can keep every one of its first arrivals alive to old age and still die if it cannot make more people to inherit the machines. Or it might be none of these individually, and instead the interaction of all of them, the web of systems tightening from every direction at once, several clocks reaching zero in the same season, each failure making the others harder to fix, until the colony can no longer keep enough plates spinning to stay ahead of its own decay. This is, in truth, the most likely ending of all. Not one clean fatal shortage, but a gradual loss of the capacity to keep up, a slow sinking beneath the accumulated weight of everything that cannot be replaced. And running underneath every one of these, quieter than all of them, is the deepest dependency of the lot, the one that is not a part or a chemical at all. It is knowledge. It is the metallurgist who dies and takes metallurgy with her. It is the physician who ages and cannot fully teach a replacement before the need arrives. It is the second and third generation, born on Mars, growing up further and further from the industrial civilization that trained the founders, inheriting libraries they cannot fully turn back into skill. A colony can have every machine it needs and still fail if it loses the people who know how to run them, and a population of a few hundred is a desperately thin vessel in which to carry the expertise of a whole species across the centuries. The most fragile thing the colony has to preserve is not any object. It is the living, practicing know-how, without which every object is inert, Step back now and look at the shape of the whole answer, because it inverts the question we started with. We began by asking how long the colonists could keep breathing. That was the wrong question, and its wrongness is the lesson. Air was never going to be the problem. Water was never going to be the problem. The problem was always the vast invisible thing standing behind the air and the water, the immense network of machines, materials, chemicals, medicines, seeds, tools, and above all, skills that quietly converts a planet's raw abundance into a life worth living. That network is not a resource you can dig up. It is a civilization, and a civilization, it turns out, is far harder to bring to another planet than 100 tons of cargo, because a civilization does not fit in a cargo hold. It lives in millions of minds and millions of specialized hands, distributed across a whole world, so seamlessly interwoven that no single person can see it, and so reliable that we forget it is there at all. Here, at last, is the thing worth saying plainly, the reflection the whole journey was for. The decisive resource on Mars would never have been oxygen, or water, or food. It would be the ability to reproduce the hidden civilization behind every filter, every circuit, every medicine, every seed, every tool, every replacement seal. Earth's greatest gift to a Mars colony was never its final cargo shipment. The last lander full of spares was the least of it. Earth's real gift, arriving invisibly inside every crate that ever landed, was the entire industrial civilization that stood behind that crate. The mines and refineries and factories and laboratories and universities, the millions of people each holding one small piece of the whole, the accumulated skill of thousands of years of learning how to turn rock into machines and machines into life. Every seal the colony ever installed was a message from that civilization. Every chip was a letter from a world that knew how to make chips. And when the signal died, what actually went silent was not a radio channel. It was the entire hidden civilization that every object in the settlement had quietly depended on, all along, without anyone noticing the dependence until it was gone. This is why the ending, when it comes, is so unlike what people imagine. There is no single dramatic breath, no gauge falling to zero while alarms wail. Here is the true and stranger shape of it. A civilization is smaller than it looks smaller, in its living reality, than the sum of its buildings and machines, because in the end, it is nothing but the connections between people who each know one thing, and the moment those connections thin past a certain point, the whole immense structure quietly ceases to function, even though every brick is still standing. That is what a Mars colony would face. Not a catastrophe, but a fading. The habitat still standing, the reactor still warm, the greenhouses still green. And a population that can no longer make the one part, mix the one chemical, teach the one skill, or raise the one healthy child that the next year requires watching, system by system, capability by capability, as the borrowed civilization they carried from Earth runs out of the ability to renew itself and cannot be rebuilt fast enough or completely enough to close the last loop. And yet this matters, and it is the note to end on rather than despair that fading is not fate. It is a threshold, and thresholds can be crossed. Everything the colony would need to reach the fourth tier exists on Mars. The elements are in the rock. The energy is in the atom, and when the sky is clear, in the light of the sun. The knowledge, at least in written form, is in the libraries. What separates a colony that merely postpones death from one that sustains a future is not the presence of resources. It is whether the settlement can convert those resources into the full, self-reproducing web of industry, health, reproduction, and preserved knowledge that a civilization actually is. A colony designed from the very beginning for that large enough to hold the skills and the gene pool, powered far beyond mere survival, built deliberately to close not only its loops of air and water, but its loops of manufacturing and teaching, and generations could cross the threshold. It could turn Mars from a place that consumes an imported civilization into a place that grows its own. It would be the hardest thing our species has ever done, and it would not be impossible. It would simply require understanding, before the silence ever fell, what the real dependency always was. Because in the end, the lesson of the silent colony is not really about Mars at all, and it would be dishonest to pretend otherwise. It is about the thing standing behind you right now, invisible and total, the civilization that made the device you are watching this on, the water in your tap, the medicine in your cabinet, the food on your table, none of which you could make yourself, all of which arrives so reliably that you have never once had to think about the millions of hands and minds that keep it flowing. A Mars colony would simply be the place where that dependency finally became visible, where the hidden web that quietly keeps every one of us alive was stripped down small enough that its every strand could be counted, and where humanity would learn, the hard way, that the last and greatest thing to run out is never the air. The colonist at the window finishes her arithmetic. She has a number now, a figure in years, and it is neither the doom the pessimists imagine nor the certainty the dreamers sell. It is conditional, like every honest answer. It depends on what they build, what they teach, whom they raise, and how much of the vanished world behind them they can coax back into being out of the rust and the cold and the abundant, patient rock. She does not know if they will make it. Nobody could. But she understands, at last, the true nature of the thing they are fighting. Not a shortage of any single resource, but the slow severing of the final dependency, the last quiet thread connecting a small settlement on a cold world to the immense, invisible civilization that was Earth's real and only irreplaceable gift. She turns off the light to save the power and goes to see about dinner. The reactor hums on in the dark, and the work of rebuilding a world begins.